This is a solution to an example problem involving index refraction and a wavelength of electromagnetic energy. In other words, a wavelength of light for this problem. So an electromagnetic wave with a wavelength of 522 nanometers in substance A is traveling between the substance A and B with an index of refraction of 1.33 and an index of refraction of 1.555. And you can see how that plays out in the diagram. How fast is the wave traveling in substance A? What is the photon's energy in substance B? And what is the wavelength in substance B? So let's look at question A first. So I'll gray out the others, and there's A. If I look at my givens, I know the index of refraction for the substance, and I know the velocity for the speed of light in a vacuum. And then by definition, the index of refraction when compared to a vacuum is equal to the velocity in the vacuum divided by the average velocity of the light going through the substance. So 1.333 is equal to 3 times 10 to the 8th meters per second divided by the average velocity of light going through the substance. This means that the average velocity of light going through the substance is equal to 2.25 times 10 to the 8th meters per second. On my paper, it would look something like this with a list of givens, the formula, numbers, and units, and then the answer with units. Let's go on to part B. In part B, I want to know what is the photon A, single photon's energy in substance B. So my strategy is to find the frequency in A, calculate the energy in A, and remember that it's the same frequency in both substances. For example, let's say one of my substances is air and the other one's water. If I'm wearing a red swimsuit and I'm in air and I jump in the pool in the water, it's still red. It may be a little more intense color, but that has to do with the transition of light between water and the fabric, between air and the fabric, but it's still red. It's not going to change color. So if the color represents the frequency in this little mind experiment is the same. That's how I know they're going to be the same frequency. So I'm looking at the givens. I've got the index of refraction of the two substances and the speed of light, in this case, in substance A, which we just calculated. I know that C is equal to lambda F, and if that's true, I also know that the speed of light, 2.25 times 10 to the 8th meters per second in substance A, is equal to the wavelength of 522 times 10 to the negative 9 meters in substance A times the frequency. Therefore, the frequency is 4.31 times 10 to the 14 hertz. But I'm not done. That's just the frequency. I got to find the energy. I know the frequency for both substances is going to be the same, so I'll use that fact to help me find the energy. Energy is equal to HF. H is Planck's constant, the 6.626 times 10 to the negative 34 joule seconds, times the frequency of the light, which is the same for both substances. It doesn't change. And that gives me an energy of 2.86 times 10 to the negative 19 joules. Now when you think about energy, another way to think about this is energy has to be conserved. It doesn't magically come from anywhere or go up anywhere. So if energy is conserved, then the frequency's also got to be conserved in this case. Alright, on paper it's going to look something like this. So there's our givens, so you can see the formula with variables, the formula with numbers and units, how it's all listed out. Now let's try to go on to part C. Question in part C is what is the wavelength in substance C? So I know that the index of refraction table is a reference to the speed of light in a vacuum, not the reference of one index to another, but the index of a vacuum. The index of a vacuum is 1. To compare the wavelengths in various substances, you must first find the wavelength in a vacuum and then compare that vacuum wavelength to the new substance. So it's not as easy as you might think. It's actually a two-step process. So I've got the index of refraction. I have the wavelength in substance A. Those are given. My first task, I want to take the index of refraction is equal to the velocity in a vacuum divided by velocity in the substance. I know that C is equal to lambda F. Since C is proportional to the wavelength, I know the index of refraction is just equal to the wavelength in a vacuum divided by the wavelength in A. That's what the C stands for, the vacuum. So now I can find the wavelength in the vacuum using this formula. 1.33 is equal to the wavelength in a vacuum divided by the wavelength in substance A. And that gives me the wavelength in a vacuum, the 6.95 times 10 to the negative 7 meters, or 696 nanometers. So that's the wavelength in a vacuum. Now I can use the index of refraction a second time to find the wavelength in substance B. So now I know the index of refraction of B, and I know the index of refraction in the vacuum, the wavelength in a vacuum. Again, same formula, index of refraction in B is equal to the wavelength in the vacuum divided by the wavelength in B. Set it all up with the givens, 1.555 equals the wavelength in a vacuum divided by the wavelength in B. So the wavelength in B is 4.47 times 10 to the negative 7 meters, which when I convert this over to nanometers becomes 447 times 10 to the negative 9 meters, or 447 nanometers. So again, problem's not so obvious. It's because we compare the index of refraction to the speed of light in a vacuum that we have to do this kind of two-step process. Now for part C, I've listed, you can see how I've done that. This is what your paper would look like for part C. I've listed my givens, and then I've described the steps that I'm taking in there as well.